So this is a follow-up lesson to the gravity lesson that we did on Friday. I'm going to quickly review what I taught you about gravity, and then I'm going to do a couple little bonus materials to add on to it. So, first thing I taught you was that gravity is a pulling force acting between two masses. That force is equal in both directions, just like any force we've talked about in this course. Sort of an extension of Newton's third law is that any force has an equal opposite reaction force, meaning any force is really two forces, one acting each way, and they're equal. So gravity is a pull, one force, pulling two objects together with the same amount of force. The more mass there is, if you increase the mass, you increase the force of gravity between the two objects. If you increase the other mass, the same thing happens. You increase this mass and you increase the gravity. And that follows a proportional relationship. So you have force of gravity versus a mass, and it's a linear value. If you double one, you double the other. If you double the mass, you double the force of gravity. And it's proportional to both. So here's M1. The same graph applies to M2. The amount of mass and the force of gravity, those are proportional to each other. The second part that we talked about today is the distance between the two masses and how gravity varies with those. So if we have two masses, one distance, we'll call that R1, and another two masses, or the same two masses, but this time they're at twice the distance. Gravity follows what we call the inverse square law, which means force of gravity varies with 1 over r squared, which means if you double the distance, then you get 1 over 2r squared, which is equal to 1 over 4r squared, which is 4 times that value up there. So you get 4 Fg over 4 for your new force of gravity if you double the distance. So gravity is inversely related to the square of the distance between the two objects. And this leads us to the proportional equation, which kind of looks, well, exactly looks like this. Force of gravity is proportional to mass 1 times mass 2 divided by the radius, and the distance between them, squared. So this follows. If you double M1, you're going to double Fg, because you're going to end up with a 2 out in front. If you double M2, then you're going to double Fg again, because you end up with a 2 out front. So if you double each of these masses, you're going to get Fg equals 2 times M1 times M2 over r squared, which is going to be 4 M1 M2 over r squared, which is, lo and behold, double the original Fg. Similarly, if you, as I've said before, double the radius in this equation, or in this proportionality, I should say. So from Fg equals M1 times M2 over r squared, we now get, let's give it like this, we now get 2r squared, which gives us 4r squared on the bottom, which is going to be 1/4 of the original force of gravity. So that is the proportion. Now the last thing we have is anytime we have a law saying that two things are proportional to each other, that means there's a constant that makes them equal to each other. So if you have Fg is equal to M1 M2 over r squared is proportional to make that an equal sign, we need to put something in here multiplying, a constant, slope. a slope for the graph that looks like this. So this slope here is a constant that we put in front to make this an equal sign. And that constant we've measured and determined to be, well, it's 6.67 times 10 to the power of negative 11. That's a rounded value. And Fg is therefore, we call this capital G. It's the universal gravitational constant, and as far as we can tell, it's true everywhere in the universe that Newton's laws apply. So we can write G m1 m2 over r squared. So this equation we can use to determine the gravitational force between any two masses, provided we know mass 1, mass 2, and the distance between their centers of mass. Next, we're going to talk about, one second while I get some numbers. Okay, I'm back. Let's just move on to the next page. Here's a graph, gravitational force versus distance. This is the one I showed you in class. You can pause this and have a look at it and see how it varies with 1 over x squared as shown in the equation there. So if you double the distance, you get 1/4 of the force. Let's take a look at this. I gave you this question in class today, but I asked you to look up some better numbers than the ones we have here. These numbers are 3 significant digits, which is usually good enough for any calculation that we're going to do, but I wanted to show you what happens when you take them to a full set of significant digits. So let's go here, and these values were actually picked up from the internet, some from Wikipedia and some from other sources. So you can go on and have a look for the exact value of Earth's mass, the exact value of Earth's radius, the exact value of constant G, and they will vary. There will be various values. There's a range that we find acceptable that we don't know for sure the exact values, but we're close. And some of these average out. For example, the radius of Earth varies. Earth actually varies depending on where you measure that radius. So if I was to ask you what the force of gravity acting on a mass, let's just call it m, at the surface of Earth. So these are the values that apply. This is going to be your r underneath. This is going to be the mass of Earth. And you're just going to use the variable m to represent the mass of the object sitting at Earth's surface. And of course, this universal constant g. When we punch these values in, we have the force of gravity acting on that object at Earth's surface is going to be equal to G m1 m2 over r squared. And if we want to revise this or change the values, this is me. This will just be m, and this will be re. So plug the numbers in, you get 6.67259 times 10 to the negative 11. Then you get Earth's mass, which is 5.97219 times 10 to the 24. And we're leaving the other mass as m. Divide that by 6.67259 times 10 to the power of negative... Sorry, that's the wrong number in. Divide that by the radius of Earth, not big G. 6.371 times 10 to the power of 6 squared. Pause the video right now and punch those numbers in and figure out what you got as an answer and see if it looks familiar to you. Okay, I'm going to assume you've stopped the pause, you've done the calculation, and hopefully you've jumped to the conclusion I want you to. We'll discuss that on Monday. Two more things. Hopefully there's time left in the video to do them. Let's have a quick look at my time. 10 minutes? Okay, I'll do one of them. We'll have time to do one. Let's talk about the units in G. Capital G. So let's put the units of this whole thing together. Fg, force, is newtons, which is kilograms, meters per second squared. Mass, of course, is in kilograms. Distance is going to be in meters. So if we put this all together, we have Fg equals G m1 m2 over r squared. So let's put this in units. Fg is going to be kilogram meters per second squared. G we don't know yet. We're going to figure that out. Kilograms times kilograms per meter squared. So let's rearrange this equation and find out what the units of G actually are. So to do that, we have to multiply both sides by meters squared. So that's going to end up on the top. And we have to divide by kilograms squared, so that's going to end up on the bottom. So we end up with G equals kilogram meters squared per kilogram squared second squared, which when you cancel everything out is going to get you meters cubed per kilogram second squared. Should be the units of G. Try that on your own. Make sure you can rearrange the units in C. We don't have to know the units for G. We don't have to be 100% on that, as long as we understand that this equation right here will give us an answer in newtons, or kilogram meters per second squared. Okay, I'm going to pause that, stop that, and we'll do another video on ratios.